Picture stacking a neural network deeper and deeper, layer upon layer, expecting it to get steadily smarter. Then something maddening happens. Past a certain depth, the thing trains worse, not better. Add more layers and accuracy actually drops, even on the training data itself. For years, the ceiling capped how deep networks could go. The fix turned out to be almost insultingly simple, a tiny piece of wiring you could describe in a single line, and it unlocked networks hundreds of layers deep. It now sits inside every transformer block running today. So what is this humble shortcut, and why does adding a value to itself change everything? Let's break it down. So why does simply stacking layers backfire? Here's the contrast laid side by side. Stack plain layers deep enough and gradients have to travel backward through every one of them to reach the early weights. Each step shrinks the signal a little, and after dozens of layers it fades to almost nothing. The early layers barely learn, training stalls, and paradoxically a deeper network ends up performing worse than a shallow one. The residual path adds each layer's untouched input straight onto its output. Now gradients have a clean route home, a highway that skips over the messy transformation entirely, so they reach the earliest layers undiminished. Signal flows freely in both directions, and suddenly depth becomes an asset instead of a curse. This single idea, first proven by ResNet, is now standard wiring in essentially every deep model. At its core, the residual pattern is a tiny loop of 4 steps. Watch it wrap a single sublayer inside the network. Start with the input, the vector arriving at a sublayer, maybe the attention block or the feedforward network. Hold on to this original copy, because we're going to need it again in just a moment. That habit is the whole trick, so keep it in mind. Now let the sublayer do its work, transforming that input however it likes, mixing tokens together or reshaping features. In a plain network, this transformed output would just march straight on to the next layer, and the original input would be gone forever. Here's the magic step. Before passing anything forward, add the original input back onto the transformed output. Output equals input plus whatever the layer computed. The layer no longer has to reinvent its input from scratch. It only learns a small correction, a residual, on top of what it already received. Finally, the sum flows onward to the next block. And because that added path carries a gradient of exactly 1, it forms an open highway straight back to earlier layers, so gradients reach them undiminished no matter how deep the stack grows. Strip it all away and 3 ideas make residual connections essential. It adds a layer's input to its output. That's the entire mechanism, one addition, output equals input plus the transformation. Introduced by ResNet for vision, it now lives inside essentially every deep architecture, wrapping both sublayers of every transformer block. It gives gradients an unobstructed highway. Because the skip path passes the signal through untouched, backward gradients flow straight to the earliest layers without vanishing, which is exactly what lets us train networks hundreds, even thousands of layers deep. The added path simply carries a gradient of 1, an open door straight to the bottom. It lets layers learn small corrections, and it can never hurt. A block only has to refine what it was handed, and if a layer has nothing useful to add, it can simply learn to output 0 and pass its input through unchanged. Alright, let's lock in what matters. A residual connection or skip connection simply adds a layer's input to its output, so the layer only has to learn a small change rather than everything from scratch. It solves vanishing gradients by giving them a clean, unobstructed path backward, which is what finally made training very deep networks possible. Introduced by ResNet, it now wraps both the attention and feedforward sublayers inside every transformer block, paired with normalization. Where you place that normalization, before or after the residual, strongly shapes training stability. Want more of the transformer, taken apart piece by piece? That's the whole project over at standarity.com. See you there.